Besides what I already told you, we are going to see a few things from our past workshop just to make sure that everything is fresh in our heads. And then we are going to see another way to categorize machine learning algorithms. Just like in science, when we study, you could have taxonomy of things. Let's say, what are the ways you could describe a human? A human could be a mammal. You could also say that the humans are bipedal because we walk on two legs. So there are different ways of describing the same thing or the same class of algorithms in this case. You could say whether the algorithm is supervised or unsupervised. Another form of categorizing these algorithms, we are going to see it just so that we understand things at the higher level as well and not just the details of implementation. And then we are going to build the Naive Bayes Classifier, which is one of the most simplest forms of classifier that we could build. And obviously, because it's a classifier, we'll be solving classification problems using it. This is what we saw in our very first video on Introduction to Machine Learning, where we said you could solve your problems in two ways. You could have either unsupervised machine learning or supervised machine learning. For supervised machine learning algorithms, what we said is we are given a set of data points. And in this case, we saw that to predict the price of a house, we were given these features or these data points. And based on these three data points, we were asked to predict what are the prices gonna be in these two cities, in Mumbai and in Pune. In those cases, what we would want to do is create our model based on these training data points. And then once we have that model, you could give it new data points and ask what's the price gonna be in Mumbai or what the price is gonna be in Pune. We said this is our training data. And again, I try to keep the terminologies minimal at first, but towards going the third lecture today, you should be quite familiar with these terms. When someone asks you what are the features, features are the parameters based on which we are building a model. These are our training data points. The thing that we are trying to predict over here is the test data, and these are the features. And the price over here is also called as the target variable. This is the target that we are trying to come out with. The price in this case is the target variable. These are the features. These are the training data points, and these are the test data points. And in the last workshop, what we saw was we were trying to do the linear regression model, which is one of the simpler ways to implement supervised machine learning. In that case, what we said was, let's say someone gave us these data points for number of hours a student studied versus the score that they have received in their exam. And what we said was, let's make a assumption. It's almost a naive assumption to make that, let's say the number of hours studied and the score that the student gets has a linear relationship. And we could see it from the graph as well. But there are some curves to it. If you had to make an exact prediction, there should be a little bit of curve to it. But over here, you are seeing that, let's say that for the sake of simplicity, let's say that to create a model, we use a straight line. We said that the number of hours the student studied and the scores has a linear relationship. And how do you represent a line in a computer's memory, or how are you going to do it? What's the general form of the model that we said is which works for any line? If we have to represent this line, yes. So y is mx plus c, where m is the slope of this line and c is the y-intercept. We said that, you know what, I can represent any line in my memory using just these two coefficients, the m and the c. If you give me this, I can plot any line on the chart or on the graph. We said, okay, the only thing that we need to do is just try out different values of m and c. The way that the actual model is going to get built is your computer is going to literally try out several different values of m and c until it reaches to a point where the distance between these points and the predictions is minimal. Y is mx plus b, and then what we said was, let's say if someone gives a point on x-axis In this case, we said that let's say someone gives us a student has studied 10 hours. You could easily plot the point on the line and then say that based on what we know about the trend, it looks like if a student studies 10 hours, he's going to score 60 marks. But then the person tells you, you know what, that wasn't correct. When a student studied 10 hours, he actually got, our prediction was 60, but the student actually got more than 90 marks. You were like, okay, so let me learn from this mistake. But the distance between what we predicted and what the actual result was, it's going to be the error in the model. If someone gives you 10 data points, you just add up all the errors that you got, and now you can get a sense of what the average or the mean error in your model is. This is what we did in the last workshop. We were trying to generate a linear model of the world based on the training data points that we had. We said that there are different ways of classifying a same thing. You could describe a human as someone who is a mammal, or you could also say a human is someone who walks on two legs. There are different ways of describing the same object, same thing. And in this case, we are trying to classify or categorize our machine learning algorithms. So one way of classifying them was, let's say, whether the machine learning algorithm is supervised or unsupervised. Another way of looking at it is whether the machine learning algorithm is something called as discriminative or generative. And what do we mean by that? Let me show you using an example of how a discriminative algorithm will go about solving a machine learning classification problem, whereas how a generative algorithm will go about solving the same problem. This is the same example that we saw in the first video, wherein we said on the x-axis we have the movie time, and on the y-axis we have the IMDb ratings of that movie. And based on these two features, we are saying that, let's say we plot all these points on the graph, and then we find that all the green points are the one that the user likes those movies, and the red points are the ones that the user doesn't like those movies. Let's see how a discriminative algorithm will go about solving it. Let's say something like a linear regression model. It is going to try to find a trend in this data. In this case, it might not succeed properly because there wasn't that much of a linear relationship between these points. And it might get confused, and it might draw a line like this. If we try some other supervised machine learning algorithms, which are also discriminative, another example of that is a gradient descent algorithm. And what it's gonna do is, in the first iteration, it might come with a line like this, but slowly it's gonna realize that this is not the best way of classifying the data. And eventually it's gonna come up with a line like this, which is best separating these two classes or these two labels. This is how a discriminative algorithm will go about trying to find the best classification. In this case, it will try out a few things and eventually reach out to a point where it has best created these two classes. Let's see what happens in the generative case. In the generative case, let's say we have the same example again. Let's not look at the green points. First, let's just look at these red points. So your algorithm is not even going to look at all the green points. It is going to look at only all the examples which have the labels as red. Because at this point, we are training the model, and the model already knows what the red points are. In the last column, the target values, we have all the reds, or the dislikes. The model knows which are the red points and which are the green points. And what we're telling is, let's say for our model, we don't even look at green points. First, what we're going to do is just look at all the red points. And based on all these red points, we are going to say, let's create our understanding of this world. In this case, we said that all these red points, they seem to lie in this area of the graph. The model is going to create this cluster, or just like you could represent a line, you could also represent an oval or a region or a curve, right? An enclosed area through an equation. We are going to create an equation in our memory, and say that, you know what, all these points, they seem to lie in this region of the graph. We are going to create this circle in our memory, and we say that all these red points, anything that lies over here, it's gonna something that we think that the user is gonna dislike. Then we look at all the green points and say, okay, based on what we know, it seems like all the green points lie in this region of the graph. And now what you could do is, based on the understanding of the world that you have created, even if you take away the training example, now if someone gives you this new point on the graph, let's say in this case, someone gave you this blue point in this region of the graph, what do you think it's the most likely result? Whether the user is going to dislike a movie or whether he's going to like it? Dislike it, right? Based on the knowledge of the world that we created, we know that all the points which lie in this region of the graph, the user is going to dislike them. This is how generative algorithm will go about solving the same problem. It's not going to look at all the points at once. It's going to look through them one label or one category at a time. An example of these two algorithms, the first one is the linear regression for discriminative algorithms, and for generative algorithms, example is a naive Bayes classifier, which we are going to see in our workshop today as well. For the points which are going to lie outside, we are going to have to make the best guess. Based on the algorithm that we are using, we could say calculate the distance between that point and the circle, and whichever is the closest, you could do that. Or in your model, you could say that your accurate, our probability of prediction, our confidence in the prediction is not good, so you are just going to select one randomly. You could either say either red or green based on how you want to implement it. Let's see, what do we mean when we talk about a naive Bayes classifier? The naive Bayes algorithm or a naive Bayes classifier obviously comes from something called as Bayes rule, and you might have heard of it. Not only heard, but we have studied it in our 12th class, and also most of us have studied in our engineering courses as well. So I'm not going to go into doing those equations and how do we derive the Bayes algorithm. But what I'm going to do is try to give you an intuition on how it's working behind the scenes. And based on that, maybe you will have a much better insight into how Bayes rule applies to supervised machine learning, rather than me trying to go over some formulas. Over here, I have an example, and let me say what I'm trying to show you over here. We have a training example from a Titanic dataset, which is a popular dataset that we are going to work on today as well. What we are saying over here is we have two classes over here. The first one is the survival, and the second one is not surviving on a Titanic accident. And we are saying that if you traveled from first class, your chances of surviving were 0.6. And if you were traveling from first class, your chances of not surviving is 0.4. If you were a male, your chances of survival was 0.5. But if you were a female, your chances of survival were little less. So it was only 0.4. And so on for the not survival as well. And over here, the bigger greens, which we are saying is, overall, your chances of survival were 50-50. The prior probabilities in this case, which is probability of survival and probability of not survival, overall is 0.5 and 0.5, with this 50-50 chance that you survive or you don't survive. But now just looking at the numbers, can you find out or just intuitively guess, will a male traveling in first class survive? Look at these numbers, look at some probabilities, these probabilities, and try to guess if intuitively that whether a male who's going to travel in first class, is he going to survive or not? The chances of him surviving are more, or chances of him not surviving are more. And again, don't try to multiply those things, and just try to come up with an intuitive answer. The chances of them surviving are more. And the reason is, we can look at this data point over here and say, let's see. First thing that we know about it is that it is a male. Over here we went and we said that male is 0.5, but over here the male is 0.5 as well. So it is still 50-50 right now. But then when we went in the first class, we saw that the chances of person surviving in first class is 0.6. And over here in not surviving is 0.4. Definitely this is always going to be greater than this calculation that we did in our head. And to formalize this, let me show you how the actual likelihoods are going to come out. What you could do is multiply these two things over here. The way you would do the math is you multiply 0.6 by 0.5 and you would multiply this by overall probability of surviving. In this case is 0.5. You would get this answer as 0.15. And then what you could do is you would multiply 0.4 by 0.5 and then you will multiply this overall probability of not surviving. In this case was 0.5. And if you multiply all these three, you will get 0.1. And because 0.15 is greater than 0.1, our classifier or our machine learning algorithm is gonna say that, you know what, based on what I know, chances of survival of this guy is more than chances of him not surviving. And over here, these are not the probabilities. Make sure that you understand that these are not probabilities, but these are the likelihood. This is the likelihood of that person surviving versus the likelihood of them not surviving. Let's do one more example and I'll let you answer on this one. We have another example over here, and the naive Bayes algorithm is very popular, especially for text-based problems, in problems where you have too many features. So for example, for natural language problems or things like spam detection, this is an example of spam detection, wherein what we are saying is, let's say if you get an email and now your email provider has to determine whether this is a spam email or not a spam email. Right now, let's make a very naive assumption that there are only 3 words in this email, and there are 3 words: money, lottery, and Code Heroku. We are just looking at these 3 words in the email. And we know from our past experience that whenever the word money has come, it is 0.6% chance that this is most likely a spam. If the word lottery has come, we know that it's 0.8% chance. So there is significantly large chance that this email is a spam. And for the word Code Heroku, it's most likely that this is not a spam. And that's why the probability of it being a spam is very less. It is just 0.01. And similarly for not spam as well. Based on what you know, can you find out if you saw an email which had the word Code Heroku money in it? Over here, the overall probability of spam emails is more. This is 0.6 and this is 0.4. In our previous example, this was 50-50. But over here, we are saying that overall, the chances of any email being a spam is more likely that a spam than not a spam. Can you look at this and try to either do those multiplications, or even you could intuitively guess, if you see both of these words, Code Heroku and money, in your email, whether it's going to be a spam or it's going to label it as not a spam. We are going to do 0.6 times 0.6 times 0.01. Yeah, that's correct on the first one. And on the second one, obviously we are going to do the same thing. We're going to select money from here. So we're going to select 0.3 times 0.95 times 0.4. And whichever is greater, we're going to say that that is the label that we're going to assign. If you do this math, you're going to get 0.036 over here. And on the second one, we're going to get 0.114. And 0.114 is going to be greater than 0.036. What we are going to say in this case is that it's not a spam. Does that make sense? I guess you get an intuition behind what we are trying to do in the naive Bayes algorithm. But can you think of a major pitfall or something that we might be ignoring when we are doing the naive Bayes algorithm over here? So look at this example in the email, for the email, and think about what are some assumptions that we are making over here. That's not an assumption that we are making, because we are saying that if there are some spam emails use the word Code Heroku, we are counting that probability over here. We know that with 0.01% chance, the word Code Heroku will occur in a spam email. So we are taking that into the account. And that's the reason. Let me show you what are some assumptions that we are making over here. The biggest assumption that we are making over here is we don't care where these words occur in the email. Even if the word money or lottery occurs in the first place, or whether it occurs in the last paragraph or the last line, we are going to count the frequency of these words. It doesn't matter whether you have the word Code Heroku as the first word or the last word. We are going to count it the same way. And the other thing that we are going to see is that the sequence of these words, let's say sometimes we are also assuming over here that the word money and lottery are independent of each other. These are the two features of the email. And we are assuming that whenever the word money comes or whenever the word lottery comes, those two are independent events and they are not necessarily dependent on each other. But if you think about it, even logically, they're like, if you take a sample of, let's say, 1 million emails, it is most likely that you are going to see there is some correlation between the emails who have the word money in them and the word lottery in them. Both of these variables, these features are going to be present in those emails. In that case, what we are going to do is count the same thing twice. We are going to add those probabilities twice, even though we are looking at the same thing, or there is some correlation between these two things, and we are assuming that the word money and lottery are independent of each other. We are giving an extra weight over in that case, and we are saying that these two features are independent of each other, and that's where we are going to count their individual probabilities as well. And that's the reason this naive Bayes algorithm is called naive as well. That what we do is we are saying that these features that we are going to look, they are independent of each other. We are making that assumption. And also the second assumption that we are making is that the order in which these features occur, they don't really matter. We are just going to count their frequencies. Was I clear on that part? Why the naive Bayes algorithm is naive? I hope that gives you a sense of how naive Bayes algorithm works behind the scenes. And again, I didn't want to go through those equations, but it is more important that you get a sense of, and intuitively you get how it works behind the scenes. What are the advantages of using the naive Bayes? So it is very simple and easy to implement, not just because we are going to use those libraries, but even behind the scenes, the implementing those, as long as you have those probabilities, once you calculate those probabilities, it becomes pretty much easy to just the matter of multiplying those probabilities together and seeing which class has more likelihood of being there, and we just select that class. So it is very simple and easy to implement. And what that does is, because it is so simple and quick to implement, it also executes very quickly. In cases where you want to do real-time detections or you want to work with a massive data set, now what you could do is now write this very simple algorithm and it is still going to do a fairly good job. It might not be best algorithm if you are looking for a great accuracy, but if you want to do something real quick, if you want to try out what the classification looks like at a high level, you can first try it out using naive Bayes and then try out some other classifiers that we are going to study in our future lectures. So it's a very good way of trying to get a rough idea of where the classes are. And then once you have that rough idea, or you could also do is use in cases where real-time aspect of it is very important. Let's say if you want to execute a model which is going to complete in few milliseconds, or which is going to run twice or thrice in 1 second. In those cases, it is going to be difficult to run something which is going to take a lot more time. And if you're trying to do a video processing or those kind of stuff, you don't want to be in a situation where you are using a machine learning algorithm which takes a lot of time to execute. Given that, I have a quiz over here. Let me go ahead and shoot the quiz. Let me go ahead and share the result as well. The naive Bayes algorithm is more suitable for cases where the speed of algorithm is critical. We just saw that if you are looking for a great accuracy, this might not be the best choice. But if speed is very critical to you, then you would want to use something such as naive Bayes to make sure that you get that speed in your comparisons or when you're doing the testing on your data. Let's go ahead and do the hands-on part for our today's workshop. The only thing that I would want to make sure is you have all these libraries installed. The other thing that I want to do is let's download the zip file for today's workshop, which has the starter code and the test data that we are going to work on. So I'm going to copy and paste this in our chat window. Go ahead and download it, extract it in the folder that where you want to work in, and then let me know in the chat that you have extracted it. Let's see what is there inside our titanic.csv file. Again, this is the same data set that I spoke about before, wherein we are trying to look at, let me just open it over here. As you see, this is the same data set that we spoke about a few minutes back. And over here, what we are saying is these are the features that we have. And our job is to predict whether the passenger is going to survive or he's not going to survive. And in this case, the 0 means he did not survive and 1 means that they survived. Our job is to predict whether the passenger is going to survive on Titanic or not based on these features that someone can give us. So you could have either their sex, their age, their whether they have any sibling or spouses abroad, or whether they have any parents or children abroad, and the fare of the ticket that they have paid. Over here again, just one more thing, that whenever you see, so for males we have a 1 and for females we have a 0. That's another thing that I wanted to make sure that you understand. And besides that, everything else should be straightforward. This is the name of the passenger and this is the fare. I don't know what the units are, what the currency is, but this is the fare that they have given us. And this is a real data set that they have from the Titanic list that they might have. That's for the data set. And let's open the naive Bayes.py file, which is the starter code that we are going to use for our today's workshop. And this is pretty much the same thing that we had in our last workshop as well for the supervised machine learning part 1, where we were doing the regression line. And over here as well, we have the same starter kit. And the only difference is in this case, we are importing the naive Bayes Gaussian model instead of importing the linear regression model from the Scikit learn library. Let's open this file and let me know once you are ready. Make sure you have looked at the CSV file and let's work on this one. Again, the first step over here is to load the data from our CSV file. So given that we have already done this in our last workshop, why don't you go ahead and load the data from the CSV file, similar to what we did in the last one, and tell me what is the line of the code that you're going to use over here. We are going to use the pandas library to import our data, and then we are going to use pd.read_csv. Let me just go ahead and do that. We are going to say data frame because we are going to load the data into our data frame. So we're going to say data frame is equal to pd.read_csv. And then we're going to say titanic.csv. Then let's make sure that we are getting the data set correctly. So we're going to say data frame.head. What head method does is it prints out the first few lines. So let's make sure we're going to say print over here, print data frame.head. And this should give us the first few lines of this data set. Let's make sure that we run this and we are getting this correct. I'm just going to wait a few seconds for this to load all the libraries. The first time it's generally a little bit slower, but then it's faster. We have the data set over here, and over here, as you see, we are printing the first few things and the first few columns. Over here, we have the data set in our program. And the next thing that we want to do is let's also just try out data frame.describe. this is going to give us the statistical properties of the data. Our library is telling us that there are 887 points in this data frame, this data set. And out of this 887 data set, the mean over here for the survival class is 0.38. So it looks like the average over here looks like bit around 0.38. And again, this is the distribution in the different classes, and we don't know exactly how the distribution for, it's difficult for us to tell using just these numbers, know how these numbers are distributed. What we're going to do next is try to visualize this data that we have, similar to what we did last time. What we are going to do is try to get the x-axis, the y-axis in our program, and then try to plot it using the matplot library. Let's try to get a few things from our data set. And over here, what we are going to say is we have a few classes over there, right? Let me make sure that I open the text file over here again. I'm going to open this text file, and let's take this first line from here. These are all the columns that we have in the data set. I just pasted over here as a comment so that we don't have to look at the CSV file again and again. And what we are saying over here is these are the different features. And to visualize it, what we're going to do is to select a few features, and based on what features we select, we are going to try to visualize the data. Because remember, it's going to be difficult for us to visualize these many features in one go. So we'll have to select 2 features at a time so that we can plot a graph out of it. And now let me ask you, my question is, based on what you know about Titanic accident, what do you think are the most likely features which is going to drive whether a person is going to survive in that accident or not? The siblings and spouses abroad, it might affect it. Definitely there is some relation between, if they have someone abroad, they might be wealthy as well. But think about what happened in the Titanic case was the richer people, they were able to get out of the ship. They could bribe the guards on the ship, and they were able to get on the lifeboats before than the people who were poor and who were in the second class. The fare of the ticket is going to have a significant impact on their chances of survival, right? Because if they have paid more, it is most likely that they were able to bribe the guards and they were be able to get on the lifeboats. What we're going to do is, let's try to visualize these 2 features. We are going to visualize the fare and their age, and we're going to see how did it affect their chances of survival. Let's extract 2 columns from this data frame, and I'm going to ask you, how are you going to do that? Let's go to the step 2 over here, and we want to do the plot data. For the plot data, we are going to extract 2 features from the data frame. Let's say ages is equal to, we're going to say data frame of something, and then dot values. What is the name of the key that I should give over here for ages, and what is the name of the key that I should give for fares? Fares is data frame of something dot values. For ages, we have the age, and for fares, we have the fare. Okay, seems like we have that. And to convert this data frame object to NumPy array, we are going to use the dot values over here. Also, let's extract the survivals. So we are going to say survived is equal to data frame of survived dot values. Last time we used the matplotlib plot.plot. Today we are going to use something called as a scatter plot. Instead of the line plot, we are going to use the scatter plot. We are going to say plot.scatter, and this is going to do the same thing. Instead, using the O parameter over here for the line style, we are going to use the plot.scatter so that we can also have some different colors over here. Let's say ages, comma, fares, and then let's make the size of this plot or each point as a little bit bigger so that we can visualize it correctly. We're going to say S is 50 so that the size of each dot over there is a little bit bigger so that we can see it properly. and then we can say plot dot show, then save it and run it and see what you see and see what you get. We made an error over here. We don't need this. It's not a method, it's just a attribute over there. So we need to say dot values and then run this. And we see a plot like this. From this, are you able to make out whether the person survived or not, or is there something that we are missing? Yep, we haven't used the survived features. What do you think? What is the best way to show the survived feature on this graph? We already have used the two axes. We already have something on the y-axis over here, which is the fares, and on the x-axis, we already have the age, which is between 0 to 80 over here. We already have those two axes over there. What might be a good way to get that intuitively, to have the third feature over there? What we could do is, instead of adding another axis or something like that, we could point the colors on these points so that if it is a red, we can say that the person has not survived. And if it's a green, we can say that the person has survived. So that might give us a good way to get the insights into the data. What we are going to do is go over here and let's add some colors. Instead of just survived being like this, we're going to also say colors. We're going to create an array of colors based on the survivals. And let me show you how you could do that in one line, or let me just do it as a simple for loop. So I'm going to say colors as an empty list over here. And then I'm going to say for every item in survived, we want to say if item is greater than 0, that means that that point is 1. If item is greater than 0, or you can let's just say if item is equal to 0, which means that they have not survived. So I'm going to say colors dot append red, else colors dot append green. If it is a 1, then we are going to append a green over here. And if it is a 0, we are going to append a red over here. Save it. And instead of just plot.scatter, we are going to say colors is equal to colors. Let's see if this works. And we made a mistake. It's a typo over there. And we get a good sense of what is happening now. By looking at the graph over here, can you tell me what is the area, or where is the region in the graph where you think that it is most likely that you will survive? Yep. So as the fare is nearing 0 over here, most of these people have not survived. And as the fare is increasing, as you see, there are more green points, and these 2 points where they have paid a lot of money, they have definitely survived. And for the age part of it, it seems to be pretty uniform. But over here, nearing the zeros, it looks like the kids were able to survive more than towards the end over here. Even in the second class or third class, the kids were able to survive more than the older people over here. That's the insight that we got from the data. And based on what we can see intuitively and what we as humans understand, we also want our computer to understand that. Let's see if we can give that same thinking capability of just what we did visually with our brains. Can we teach this to our computer as well? Can we teach this to our machine learning algorithm as well? Let's go ahead and do that. Let's close this. I'm going to comment out these two plots so that we don't get confused. I'm going to comment these both plots. We were able to now get a good sense of what is happening in the data. And now once we know that, let's go ahead and prepare our training and test data sets as well. Let's go ahead and go over here and say building a model part. What we're going to say is we are going to create two sets over here. The first one would be our features and the second one will be our target values. Based on what we know from our supervised machine learning introduction class, we have two types of columns. The first type of column we have is a feature column, or you could have a target value that we are trying to predict. Let's do our features over here. So we're going to say features is equal to, we are going to say for the features, we want all the columns in our training data set except for our target value. What is our target value over here? What is the target column? What are we trying to predict, or what is the class that we are trying to come up with? Survived, right? So that's the target column or the target we are trying to come up with. For the features, we don't want that target. We're going to say data frame dot drop. We want to remove that. And this is how you do it. You want to remove survived. And then you're going to say axis as 1. What this does is it's just saying it as remove it from the first axis over there. And then we're going to say values, just like we did before. And then we're going to say target is equal to data frame of survived. We already had it before over here as well, the survived as same thing, but let's just name that as targets so that we know what we are referring to. And then what we want to do is let's divide this entire data set into two parts, the training data set and the test data set, just like what we did before. And over here, we know that there are about 887 data points. And if you do the math and you take 80% of that, you will get a number around 7110. What you want to do is let's take the first 710 points as our training data. I'm going to say features train, comma, I'm going to say target train is equal to features of 0 to 710, comma, targets of 0 to 710. And over here, we're going to say features of test, comma, targets of test is equal to features of 710 till the end and targets of 710 till the end. Let's just print these out so that we know we are getting everything correctly. I'm just going to print one of those things. So I'm going to say features.train. Let's see what do we get over there. I'm going to run this. Let me make sure that I get the capitalizations correct over here. So I'm going to say train. And let me make sure that I don't use the values over here right now. Let's remove the values for now. And the first thing that we see is we are getting until 0 to 709. For the features test, we should get from 710 to 886. We are getting all our data points in there. Let's add the values over here again so that we know that we would need the NumPy array instead of the data frame object. Over there, what we saw was the indexing was not working correctly. I'm not sure if that was the case with the CSV file, whether we were missing, we had an extra line character over there. There was something off over there, definitely. And for this one, when I was trying to inspect over here, we were getting the, even if we do the normal indexing, just like we did, like we do in our Python array or Python list, it was working fine. I'm definitely not sure if you could figure out and tell me what was going wrong in the last session, and that will help, because I looked at the CSV file and I think it might had an extra line character in there because of which we were missing it out. All right. So we were able to separate out both our training data and test data. The next thing that we are going to do is build the Gaussian model and try to fit the training data inside to our Naive Bayes Gaussian model. I already have that example in the comments in the top over here. Why don't you try that out and tell me what are the 2 lines of the code that you're going to use to generate the model, and then try to fit this training set that we have inside our model. What are the 2 lines of the code that we need to write? The first one that you need to use though is, first you need to build the model as well. You're going to say model is Gaussian Naive Bayes, and once we have this model, what we could do is fit it. So we're going to say fit the data inside the model. We're going to say model dot fit features train, and see how easy it was, because if we name our features correctly and the training and test data sets correctly, it becomes very intuitive to when we are using it in our program as well. When we are saying model.fit, we are training the model. So it is obvious that we want to give the features and the target values. And we are going to give the both the training points. We are going to say target train. It becomes very simple for us when we are trying to do those operations in feature if we name these things correctly over here. And once we have this thing over here, let's see how can we predict it. What we could do is say model. Let's print this thing, print model.predict. What is the list that I should give for my predictions? We need to give the features which are in our test data points. We're going to say tested based on the features in test data points. Save it, and then let's try to print this out and see what do we get. We are seeing that our model is complaining that it could not convert the name of this guy to a string. What do you think we should do now? First of all, do you think that the name of the person makes any sense for us in trying to predict whether he survived or not? Is it important to preserve this feature? It doesn't make sense to keep this. What we're going to do is go on the top over here, just like we dropped the survived features in the feature set. What we're going to do is right at the point where we are reading this thing, we are going to remove from the data frame these columns which we don't want. We are going to go over here, and instead of having this over here, just right after the read CSV, we are going to say data frame is equal to data frame dot drop. We don't want these things. And what do we don't want? We don't want this column. So the name of the column is name. We don't want this feature over there. So we are going to go back to the top and remove this name from our data frame completely so that it doesn't affect our model. Save it and then run it again. And it is complaining that it can't find the word name over there. We want to make sure that we also give axis as 0, just like we did on the first one. So we're going to say remove it from the first axis over there. And now we have something. We are getting the predictions over here for the survivals that we are trying to see, but it is not that helpful right now. We just see zeros and one. Let me ask you, what will you print out so that you can compare if the model is performing accurately or not? Right now we are just printing out the predicted values. What can we print out along with these predicted values, so side by side, so that we can see both of them and see if our model is working correctly? One approach you could do is print those mean square errors, but even to generate those mean square errors, you will need to compare this predicted values with something. What do you compare the predicted values with? The test points, right? The target tests. What we're going to do is let's print the target test and the predicted values side by side so that we can see if it is performing correctly. What we're going to do is come over here and let me write this thing over here. Even before we do the error estimation, we're just going to print out both of these things side by side. So instead of just saying print this thing out, we are going to say these are the predicted values. Predicted values is equal to this thing. And then over here, we are going to say for X in zip, we want to show two things side by side. And that's why we are using zip over here. Let's say the actual is the test targets. So we're going to say target test, comma, predicted values. We're going to print both of these side by side. And then we're going to say print actual was X of 0. If you don't want to use X, maybe we could use an item over here. Item of 0, and the predicted was item of 1. What we are saying over here is print both of these values side by side, and to print both of them side by side, we use the zip over here, which will combine both of these in one tuple. And we are going to print both of these things side by side so that we can see if we are doing, if our model is performing good. Save it and then run it again. As you see over here, now we could see both of these things side by side. Actual was 0, predicted was 0. Over here, it seems that we are doing good. 1 was 1. And in some cases, we are making an error. For example, in this case, the actual was 0, but we predicted 1, which means that the actual was like the person did not survive, but we predicted that the person survived. It still gives us a sense that we are doing good, because a lot of these cases, you are saying that majority of these cases we are performing quite good over there. Let's just get a number out of it instead of just trying to visually do it. Let's get the error rate. By comparing these two, we know that we can get the error rate, and you could do it in a for loop as well. But what we are going to use is, there is a method that Scikit learn models provide us to evaluate our models. Directly what you could write is, instead of trying to compare each, you could compare both of these elements and then count how many times you did not perform correctly or how many times you were off, and then you can get an average. Or a simpler way is to print model dot score. We are trying to get the score of this model, and we are going to use these two things, the same things that we had before in our target over there. Let me just make sure that I get these two things correctly, and I'm going to say model.score target tests. Let me just look at the documentation as well and make sure that I'm getting this correctly. I'm going to say scikit-learn model score. We want to quantify our model, and we are going to use the model.score method over here. Over here, you could see is they are using the score method. I'm trying to find an example where now they have used the score method, so that we want to make sure that the parameters that we are giving are the right matrices over there, or the right lists over there. They have an example on this one, so let's see. Over here, what they are saying is, if we need to score it, we are going to give it the X and the Y, which are the test data points. What we want to do is now give the test data points over here. Let's try to give our test data points. Both of our test points, we are going to give it over here. What were our two test points? We had the features test and the target tests. What it is going to do is, behind the scenes, it is going to run the predictions and get these features test and the predicted values. So we don't have to give the predicted values over here. What we need to give it is both are the test data features and the test targets, and in behind the scenes, it is going to run the predictions and then try to evaluate if we're correct or not. Let's go ahead and run this, and let's see what do we get. And as you see, we get an accuracy of about 81.9%, which is not bad at all for a model that we could quickly build. Let me just also make sure we print this out. Accuracy is, we printed this thing out over here, and we saw that the accuracy of this model that we have is 0.819 or 81.9%. 81.9% of time we were able to predict if the person is surviving or he is not going to survive based on the features that we gave. Do you have any questions on why did we do something? Because in the last part, I had to look at the documentation over there just to make sure that we were giving the right lists over there. But was that clear on why did we give the test features and the test targets over here? Because it is going to call the predictions behind the scenes. The model.score is going to call that, and we just have to give the features test and the target tests. So let me know if you have any questions on this one. Yes, the model.score is doing exactly what you said. It is going to create the predictions out of the feature test, and based on the predictions that the model is going to make, it is going to then compare it with target test, just like we were printing it out over here. And then if there was an error, it is going to increment the count in its memory. We could do it ourselves as well in this for loop, but it is easier way to just do it using model.score in our future programs as well. That's it for our today's workshop. Hopefully you got something out of it, and we want to make sure that everyone in our workshops walk away with the sense of being able to create something. And I hope I was able to deliver that. Our main objective over here is to try to reach as much of people as we can. If you know some of your friends who might be interested as well, get them along as well next time. And if you haven't already reviewed us, make sure you go to our Facebook page and review us, and so that we can get more audience in our workshops. Also tells us how we are doing in our workshops. Thank you. Bye.